Today, basically we're going to just try to put the stuff we did last week all together. So really this week will pretty much consist of working problems in class. If you're sitting there and you have, if you're sitting there and you have books or notes or whatever you have from, I mean, I guess you should have your own notes. Feel free to look at it. Like I say, when you guys work problems, when you start working problems in a topic, you should use your book, your notes, all that information. The best way to learn that information is to use it in a problem, right? So if you consult those notes, you'll figure it out. So the question here is, what is the product? And by which mechanism that we've done so far. Right, so this is going to be SN1, SN2, E1, E2. And no reaction, hang on, no reaction, you should keep no reaction in mind. No reaction is always, you're not automatically going to get a reaction when you mix chemicals together. I'm going to take that off the board for this one. Something will happen here. Yes?
It's fine. I looked back on my notes. I was remembering you said something about temperature in between E1 as in when it's higher temperature.
Yeah, temperature tends to favor, higher temperature tends to favor elimination.
Okay.
I don't know if you guys can read that or not. SN1, SN2, E1, E2, no reaction. How's it going? All right, so for Chapter 7 reactions, and this is really the case for any chemical reaction. As you look at a set of reagents, right, you want to classify it as best you can. So what type of molecules do you have? What kind of chemistry do you know that type of molecule does? And then that narrows down to questions, specific questions you need to ask about that type of reaction. Okay? So right now, it's not true that Chapter 7 are the only reactions you guys know. You've seen acid-base reactions. So you can ask, do you have a strong acid? Do you have a strong base? Anyone want to venture a guess on that? Sulfur's probably throwing you off a little bit. Do you have a strong acid? Okay, I see some tentative shakes of head. You don't have a strong acid here. Water is both a weak acid and a weak base. The sodium is going to be plus, the sulfur is minus. Turns out the pKa of the conjugate acid of sulfur minus is somewhere in the vicinity of 8. Okay, so the conjugate acid of that sulfur anion is not a real strong acid. So that means it's going to be a decent-ish base. Like the sulfur minus is an okay base. It's not as strong a base as an O minus. But we'll come back to that. So probably not going to do an acid-base reaction. You don't have a super strong base and you don't have a strong acid. There's not really any protons or atoms in this molecule that would do anything. So in chapter 7, the question is, first question should always be, is there a leaving group? All right, more. Yes, there is a leaving group. Say here, good nucleophile. So is there a good nucleophile or a strong base? Right, so that's the one, there actually is. And this is the one where we come back. So nucleophilicity increases down the periodic table. Okay, so hydroxide, we've done hydroxide. Hydroxide is both a strong base and a good nucleophile. So we covered that last time. Nucleophile, base, strong, good. SH, so S minus, right? As you go down the periodic table, the nucleophilicity has to increase. The reason for that is the atom is more polarizing. Okay, so the valence electrons, the electrons that are actually doing something, the electrons that are going to come in and make a new bond to the carbon, those are farther from the nucleus, right? So they're farther from the positive center that's holding them in the atom. And that makes them more susceptible to positive centers that float by, right? So in terms of the nucleophile here, SH is going to be a better, or a negative S will be a better nucleophile than a negative O. But then it's a weaker base. And there's quite a bit that goes into this. The SH bond is not as strong. Generally speaking, atoms make stronger bonds with other atoms that are about the same size. Can't remember how much we went over this at the beginning of the semester. Sure, I mentioned it some in passing, but probably not enough to really stick, right? For a bond to form, these orbitals have to overlap. And so I like to use an analogy of a handshake for a bond, right? That's a sigma bond. So think about shaking hands with like a 2-year-old, right? It's always a little awkward because your hand dwarfs their hand. It's not a real firm bond. And the analogy falls apart a little bit because, right, you have a gripping hand. The 2-year-old will like fall. You wouldn't handshake them. You would just grab their arm and hold on to it. So you can hold a 2-year-old really firm. Atoms aren't like that. So this tiny little 1s orbital for hydrogen is going to encounter, like the Death Star in this big atom. And that's going to make for a weak bond. All right, as you go down, then, if you had selenium, so selenium minus is going to be an even better nucleophile and an even weaker base. So one thing, nucleophiles, remember the leaving groups. You guys probably at this point, if you've looked at this material at all, have learned the leaving groups. Chloride, bromide, iodide, sulfonate anions. That's basically it in chapter 7. Okay. Nucleophiles take on a lot of different types. So anything that's a strong base, a strong Bronsted base, if it's sterically small, will probably be a good nucleophile. So that's easy enough. If you can recognize a strong base, that's got a good chance of being a strong nucleophile. But then there's all these ions and atoms that are good nucleophiles without being particularly strong bases. And that takes a little bit more, and you should look at it. There's tables and stuff in the text, in the handouts, in the Chapter 7 modules. But some of it is you just kind of want to ID it. So some good nucleophiles that aren't real strong bases. And when I say strong base, I mean Bronsted base. So azide ion, N3 minus, so this is azide ion. It's not a real strong base, but it's small. So it's got a lot of electron density. The electron density is really sterically exposed. It's kind of bullet shaped. And so it turns out to be a really good nucleophile. For a lot of the same reasons, cyanide is a good nucleophile. Again, it's bullet shaped, it's small. What else? Phosphines tend to be good nucleophiles. Remember, so we don't have a periodic table in here, but phosphorus is just below nitrogen. So nitrogens are strong bases, like amines are strong bases that make some pretty good nucleophiles. If you go down to phosphorus, that's going to be a better nucleophile. Same argument with the sulfur and the oxygen. And then actually, this is weird. I still think this is weird. All right, iodide, bromide, and chloride, these are good leaving groups. So it seems like if you're a good leaving group, it shouldn't be a good nucleophile. But it turns out they are. Now, thermodynamically, right, an iodide's not going to come in and kick something else out because the iodide's, it's a good leaving group. But if they need to displace each other, they can. So iodide displaces bromide, bromide displaces chloride. Are there others? So basically, any sulfur anion, or even really a neutral sulfur, is a good nucleophile without being a real strong base. I might be forgetting one. I should have written these down before I came in. Okay, so point is though, this is a good nucleophile that is not a strong base. So I'm going to give you another minute or so. If you'd come up with a product thinking, oh, there's not a good nucleophile or a strong base, I'm going to let you amend your answer. The other, sorry, before you amend your answer, there's another question you got to ask. Are there beta hydrogens on this molecule? Yeah, there are. Okay. So carbon of the leaving group is alpha. There's one beta carbon. It's got two hydrogens. So what that means is elimination is possible. Okay. So without a leaving group, we cannot do any of these four reactions: SN1, SN2, E1, E2. If there's a good nucleophile or strong base, you go one direction. If there's not, you go another direction. If there are no beta hydrogens, you couldn't do elimination. So the fact that there are beta hydrogens means that elimination is possible. All right, so like I said, those three questions you should just ask every time you encounter a Chapter 7-like reaction. So right now, I know it doesn't seem like it, but you have a bit of an advantage in that, you know, on exam 2, the only reactions you're going to see are either going to be Bronsted acid base from Chapter 3, or they're going to be Chapter 7 reactions. So that's all you have to ask. In the lab, if you're working as an organic, you're working as a chemist and you go to mix chemicals, you have to consider all the reactions. Okay.
How can you tell the biggest difference between SN2 and E2?
SN2.
E2.
Oh, okay. That'll be part of the answer. So you're struggling with the. All right. Anybody want another minute or so? Okay. So there is a leaving group. Bromide's a leaving group. The next question is, and this is a big one, is there a good nucleophile or a strong base? And the fact that there is means we're going to do SN2 or E2. So there's a flow chart in the chapter 7 module that I put together. Takes you, it's convoluted, and look, there is a lot of information. That's why I preach that you've got to practice these, okay? Because it will make sense after you do a bunch of them. All right. So SN2 and E2 are driven by the nucleophile or the base. SN1 and E1, right? The rate limiting step, the step that initiates the reaction, is the leaving group leaving. Having a leaving group, even if it's a good leaving group, having it just like leave to give a carbocation and the leaving group anion, that's slow. Okay, that's going to be an intrinsically slow process. So SN2 and E2, if they're possible, will be faster than that. But they're only going to be possible if you have a good nucleophile or a strong base. So again, we have a good nucleophile here, but it's not a particularly strong base. And so the question was, how do you differentiate SN2 and E2, right? So the fact that we have a good nucleophile or a strong base tells us SN2 and E2. Then how do we split that? So in this case, SN2 or E2. So E2 is driven by a proton transfer, so you need a strong Bronsted base. Here we don't really have one, so this is going to favor favors SN2. The other is temperature. So this is true for E1 and SN1. It's also true for E2 and SN2. A higher temperature favors elimination. And this has to do, it's in the book, it's in the video from either, I think we talked about it on Friday, I can't remember. When you do an elimination, you actually create more disorder. You break apart a molecule. One molecule turns into two molecules. That drives disorder. Entropy increases. Entropy is a more important factor at a higher temperature. So if the temperature is higher, you're more likely to get elimination. Now, the other thing there is you have to be able to do an elimination, right? So if there are no beta hydrogen, it doesn't matter what temperature you do it at. It doesn't matter how strong a base the nucleophile is. Without a beta hydrogen, there's no elimination. Okay, so here it's 25 degrees. Is 25 degrees low? Is it high? I kind of arbitrarily tell you in that flow chart, I think it's 40. So if you do a reaction above 40 degrees C, that's high. 40 degrees C is about 100 Fahrenheit, right around body temperature. Again, like all this is really, that's a very muddled thing. Like I want you to learn the principle that the higher the temperature is, the more eliminations favored. Like that will pay off in biology and physics and chemistry. Learning which reactions, like I've never done the reaction here. So with this molecule, it could be that 25 is a high temperature, and if I had a strong base, I would do E2. It could be that I could put a strong base in and go up to 100, and this is going to do SN2. It really depends on the molecule. So that's why I kind of give you that 40 degrees is high. I'm sort of tipping off. This is how I'm going to test you if you know higher temperature favors elimination. I'll tell you it's 80 degrees, and if that makes you think elimination, that's good. The other thing you have to consider here type of carbon the leaving group is on. Okay? In this case, this is a primary alkyl bromide. So you guys need to be able to recognize that at a glance. The carbon with the leaving group only has one other non-hydrogen thing on it. So this is, alpha is primary. And we write that as 1 degree. I don't know why that got started, but that's the way we do it. So the bromide's on a primary carbon. Primary carbons can do SN2. Keep in mind, there's no SN2 on the tertiary carbon, and that SN2 is slower on a secondary carbon.
Could you explain primary, secondary, tertiary real quick?
Yeah. So all right, so if the carbon the leaving group's on is bonded to one other carbon, we call it a primary carbon. That's a primary alkyl bromide. If this was an OH, it would be a primary alcohol, etc. Secondary, secondary carbon's going to have the leaving group. The leaving group's going to be on a carbon that's got 2 alkyl groups. And a tertiary would be the carbon with the leaving group would have 3. Right? And so the more sterically hindered that carbon with the leaving group gets, the slower SN2 is going to be. So if you're trying to decide, if you've kind of come down to, hey, this reaction could be SN2 or E2, could be either one. I've got a good nucleophile that's also a strong base. I've got beta hydrogens. I'm not sure what it is. Temperature is kind of in between. Well, if the leaving group's on a tertiary carbon, it's an E2, straight out, right? Because it can't do SN2. If the reaction's either SN2 or E2, it's easy, right? It can't do SN2, it's going to be E2. Same thing, if there are no beta hydrogens and it's SN2 or E2, it's got to be SN2. Okay, so this is a primary alkyl bromide. The main thing in this reaction that I've got on the board right now is this one. The nucleophile is not a strong base. So sulfur is a much better nucleophile than it is a base. And so this is going to favor SN2. The temperature also favors substitution. And the carbon the bromide is on is primary, so it's sterically relatively open, and it can do SN2 pretty well. So this is going to be an SN2 reaction. I'll fill that in so you can read it. And so now you have to get the product, the mechanism and product. The SN2 is a concerted attack. Sulfur electrons attack the alpha carbon. So the sulfur alpha carbon bond forms simultaneously as the carbon bromide bond is leaving. All right. So go ahead and draw that product. If you have it, if you had it already, congratulations. If you don't, go ahead and draw that. Okay, so we're gonna get an S carbon bond. The other thing the reason I put some other chiral centers in there, very commonly, and I would like you to do this, you should memorize, if not fully understand, why an SN2 reaction gives inversion of configuration. So, but that's only on the carbon that's attacked. Okay, so we're only going to get inversion of the stereochemistry on the alpha carbon. Now there's no stereochemistry there this time to invert. It's an achiral carbon. It's got 2 hydrogens on it. So you're not going to be able to tell in the product that this had to be a backside attack with inversion. But it is. But the other thing is, a lot of times, I used to do this thinking it was just obvious and I didn't mention it in class. Right? If you just memorize inversion of configuration with an SN2, but not that it's only on the carbon that's attacked, you might draw here, you might put a wedge there and a dash there, thinking everything inverts. Right? So here's something else, and this goes to chapter 6 in the discussion of curved arrow mechanisms. If there's not an arrow to an atom or from an atom, nothing happens to it. Right? right? So any atom, any bond that breaks or forms has to be accounted for with a curved arrow. Right? There are no curved arrows anywhere near these two chiral centers, so nothing's going to happen there. You just copy that over. Okay, so the product would be and you always want to count your carbons and everything. And so bromide is going to come off. And if you like, that sodium, the product you're going to get here would be sodium bromide. The other product, the inorganic product, would be sodium bromide. Okay, so the sulfur attacks the alpha carbon. Sulfur electrons make a bond to the alpha carbon. And again, really this is a backside attack. The sulfur would have to come right here. Carbon bromide bond breaks. There's your product. And again, if you want to think about it in terms of energy, the carbon bromide bond is much weaker than the carbon sulfur bond. And then if you think about base strength, bromide anion is a much weaker base than sulfur anion. Okay? Sulfur anion is not nearly as strong a base as hydroxide, but it's still a good bit more basic than bromide. So the side that's favored has the weaker base. Any questions about that reaction?
Yes. So which side is favored again?
The right.
The right. Okay. And that's because the base is weaker.
Yeah. So there's a couple of things on here that I haven't really. Okay. So we mentioned the temperature. The temperature is going to give you information about elimination versus substitution. It's not dispositive though, okay? You can't just look at the temperature and say, this is going to be elimination. You certainly can't look at the temperature and say, this is going to be E2 versus E1. Or SN1 versus SN2, okay?